What if the most powerful forces in the universe don't announce themselves at all? We tend to associate importance with light, motion, or noise. Yet on cosmic scales, influence can be quiet, steady, and almost invisible. Some of the universe's deepest structures reveal themselves not through spectacle, but through the slow, consistent way everything else responds. If you enjoy calm explorations like this, you can support the channel by liking and subscribing. Now, let's begin. At the quiet center of our Milky Way, far beyond familiar constellations and softened by layers of dust and starlight, there exists something we cannot see directly. It does not shine, and it does not glow, yet its presence outweighs millions of suns, shaping the paths of everything nearby with a steady, unseen pull. This hidden presence is known as Sagittarius A star, a supermassive black hole resting at the heart of our galaxy. Compared to the blazing engines that power distant quasars and active galaxies, it seems almost shy. It rarely flares. It makes little noise, but that calm surface hides a place where gravity tightens space itself, where magnetic fields twist and snap, and where the familiar rules of physics are stretched thin. For most of human history, even knowing where to look was impossible. Long after telescopes began opening the sky, the center of the Milky Way remained concealed. Astronomers could trace planets, follow the motions of nearby stars, and chart wide regions of the heavens. But whenever their instruments turned toward the densest stretch of the Milky Way, toward the constellation Sagittarius, their view dissolved into confusion. Light blurred, shapes overlapped, dark lanes cut across bright fields like smoke drifting through lantern light. What stood in the way was not emptiness, but excess. Too many stars, too much dust, too much matter pressed together in a swollen core, now called the galactic bulge. This bulge is a vast central thickening made of hundreds of billions of stars, piled together more tightly than anywhere else in the galaxy. From Earth, it lies directly in the direction of the galactic center. Yet seeing through it proved nearly impossible to the unaided eye. The Milky Way appears as a pale band stretched across the night, like a faint cloud brushed onto darkness. But that glow is not mist. It is starlight, countless stars packed so closely that they blur into a single soft sheen, brightest toward the center, where their numbers increase. Along with that brightness comes a deep, persistent darkness, not a lack of stars, but the presence of dust. Between the stars drift vast clouds of interstellar dust, made of tiny grains of carbon, ice, and rock, remnants of ancient stars long gone. Each particle is small, almost insignificant on its own, but spread across immense distances, they become powerful. They scatter and absorb visible light, the kind our eyes and early telescopes rely on. For centuries, astronomy was limited to this narrow window of light. Telescopes were, in essence, carefully crafted extensions of human sight, and human sight cannot see through dust. Nowhere is this problem greater than toward the galactic center. When astronomers gazed in that direction, they encountered a wall, a layered barrier of glowing stars crossed by dark streaks, hiding whatever lay beyond. Nearby stars stood out clearly, but behind them, light faded into shadow. The true center of the galaxy remained unreachable, as if a curtain had been drawn across it. The bulge itself deepened the mystery. Unlike the flat, disk-like spread of stars that form the galaxy's outer regions, the bulge is round and thick. Stars overlap, shine from every direction, and blend together until individual signals are lost in the crowd. Because of this, the Milky Way's heart became one of the sky's great unknowns. Astronomers could map spiral arms and chart nearby stellar neighborhoods, yet they could not say what lay at the center, or even if there was a center at all. Some early observers believed the sun must sit near the middle, simply because stars seemed evenly distributed in every direction. Their view was shaped by what they could not see. Dust hid the true center, making the galaxy appear more uniform than it truly was. In the 18th and 19th centuries, astronomers such as William Herschel attempted to map the galaxy by counting stars, assuming that more stars meant more matter, and fewer stars meant empty space. Without knowledge of interstellar dust, their maps suggested an uneven, lopsided structure. In reality, vast regions were simply obscured. It was not until the 20th century that this veil began to lift. The change came with a quiet realization: light exists in many forms. If visible light could not pass through dust, perhaps other kinds could. Infrared light and radio waves, invisible to human eyes, travel more easily through dusty regions, carrying information without being scattered as much. By learning to detect these forms of light, astronomers gained new ways of seeing. Infrared telescopes revealed stars hidden deep within the galactic bulge. Regions once thought empty glowed with activity. Radio telescopes, sensitive to even longer wavelengths, detected signals from places no optical instrument could reach. In the 1930s and 1940s, radio astronomers noticed something unusual: a strong, persistent radio signal coming from the direction of Sagittarius. It did not behave like a normal star. It did not match anything familiar. It was simply there, bright and steady, buried deep within the galaxy's core. They named it Sagittarius A. At first, it was just a point on a radio map, but as instruments improved, that point began to stand out. Something massive seemed to reside there, something unseen, something exerting a powerful pull on its surroundings. Stars nearby moved at remarkable speeds, hinting at a deep gravitational well. Even so, dust and gas continued to complicate observations. To study the galactic center, astronomers built ever more precise instruments, working from mountaintops, from high-altitude balloons, and eventually from space itself. The bulge remained crowded, restless, and difficult to untangle. What made the challenge even greater was motion. Stars near the center do not drift gently. They race along tight paths, circling an invisible focus. Tracking these movements requires patience measured in years. Only by watching the same stars over long stretches of time can their paths be traced and patterns revealed. Dust, density, and speed all work together to keep the truth hidden for most of human history. The breakthrough began quietly, not in an observatory, but in a practical engineering problem. In the early 1930s, a young engineer named Carl Jansky was working at Bell Telephone Laboratories in New Jersey. His task was to investigate mysterious static interfering with long-distance radio communication. To trace the source, he built a rotating antenna mounted on wheels. Able to sweep the sky, it detected radio waves in the shortwave band, around 20.5 megahertz. As Jansky listened, patterns emerged. Some interference came from nearby thunderstorms, some from distant lightning, but one signal returned again and again, rising and falling in a cycle that repeated roughly every 24 hours. At first, it seemed linked to the sun, but over time, the timing drifted. The signal arrived about 4 minutes earlier each day, matching Earth's rotation relative to the stars. Not the sun. The source was cosmic. The signal pointed toward the center of the Milky Way. For the first time, radio waves from beyond the solar system had been detected. The discovery was accidental, a byproduct of routine work. It did not immediately transform astronomy. Jansky himself moved on to other projects, and his antenna was eventually dismantled. But the idea had taken root. A few years later, Grote Reber, a radio engineer and amateur astronomer, built his own radio telescope in his backyard, a large parabolic dish roughly 9 meters across. It allowed him to scan the sky systematically. Reber confirmed Jansky's findings and created the first radio maps of the heavens. Once again, the strongest signals traced back to Sagittarius. Through the 1940s and 1950s, radio astronomy grew. Antennas became larger and more sensitive. The invisible sky revealed itself. Regions dark in visible light glowed in radio waves. The Milky Way's center, once silent, spoke in this new language. By the 1960s, radio telescopes uncovered gas clouds, remnants of stellar explosions, and distant galaxies. Yet one source remained especially compelling: the compact, steady radio signal at the galaxy's core. This signal was confined to a remarkably small region, suggesting an object both compact and powerful. It did not flicker like a star. It did not expand like a nebula. Even by the 1970s, its true nature remained uncertain. To understand it, astronomers needed to observe the motions of stars orbiting nearby. That meant waiting, measuring, and returning night after night. The center of the Milky Way lies about 26,000 light-years away. Even fast-moving stars there reveal their paths slowly from our distant vantage point. At the same time, infrared astronomy continued to advance. Early efforts used high-altitude balloons and aircraft to rise above the thickest layers of Earth's atmosphere, which absorb much of the infrared light. Later, telescopes were placed on high, dry mountaintops, where the air is thinner and clearer. From these quiet summits, astronomers began to see through the dust. Clusters of stars emerged where darkness once ruled. The galactic center revealed itself as a place of intense activity, not absence. Still, Earth itself posed limits. Heat from the planet and lingering atmospheric interference blurred certain wavelengths. The next step was to leave the ground entirely. In 1983, the Infrared Astronomical Satellite was launched, mapping the entire sky in infrared light. Regions once thought empty lit up with warmth and structure. Later missions, including the Spitzer Space Telescope, launched in 2003, looked deeper still, with instruments cooled to extremely low temperatures. Spitzer detected faint traces of heat across the galaxy. Among its most compelling targets was the Milky Way's center. Through its infrared vision, Spitzer observed stars moving in tight, rapid paths around a dense, unseen point already known from radio observations as Sagittarius A star. Now, watched in a new and revealing light, but still from a great distance. While Spitzer watched from the quiet cold of space, the work on Earth was deepening as well. On the high, dry plateaus of Chile, at the European Southern Observatory's very large telescope, a team led by Reinhard Genzel spent years returning to the same patch of sky, night after night, season after season. They followed faint points of infrared light moving against the background glow. At nearly the same time, half a world away in Hawaii, another group led by Andrea Ghez was doing the same with the Keck Observatory. Different mountains, different instruments, the same patience. Both teams were learning how to see through the dust, how to separate one star from another, and how to listen to motion rather than light. The stars they tracked lived dangerously close to the galaxy's center. Some of them completed full orbits in only a few years, racing along paths far tighter than anything seen elsewhere in the Milky Way. These stars became quiet messengers. Their movements carried information about something they could not see directly. One star, later known as S2, followed a long, fast loop that brought it astonishingly close to Sagittarius A star. Each pass was like a whispered confession, revealing how strong the pull at the center truly was. By carefully tracing that path over time, both research teams arrived at the same realization. The unseen object tugging on S2 had the mass of about 4 million suns. Yet it was confined to a region smaller than our solar system. It did not glow like a star. It did not spread like a cloud. There was no known object that fit those conditions, except one: a supermassive black hole. None of this clarity would have been possible without infrared astronomy. Visible light still faltered at the galactic core, scattered and swallowed by dust. But in infrared, the story sharpened. Heat appeared where eyes saw darkness. Stars traced elegant, relentless arcs around an invisible center. The shape of the galaxy's hidden heart slowly emerged, not as a void, but as a place of intense order masked by chaos. With the right instruments, astronomers could measure stellar positions to fractions of a second of arc. Angles so small, they seem almost imaginary. Yet when followed across years and decades, those tiny shifts told dramatic stories. In the 1990s, the long-term effort truly began. Reinhard Genzel's group, working through the Max Planck Institute in Germany, and Andrea Gez's team at the University of California, Los Angeles, committed themselves to watching, waiting, and measuring with extraordinary care. Even infrared light had to fight its way through Earth's atmosphere, which causes stars to shimmer and wander slightly in images. To counter this, astronomers turned to adaptive optics, a technology that adjusts telescope mirrors in real time to cancel out atmospheric distortion. With this steadying hand, the motions near Sagittarius A star came into focus. There, stars were not drifting. They were hurtling. Some moved at speeds of several thousand kilometers per second, fast enough to cross the distance from Earth to the Moon. in a little over a minute. Among them, S2 stood out again, bright, persistent, and obedient to gravity. It traced a clean elliptical path, the same kind of shape planets follow around the Sun. Over 16 years, S2 completed a full orbit. No star so close to the galactic center had ever been followed with such precision. Its path allowed astronomers to weigh the invisible object at the center with remarkable confidence. The result never wavered. Roughly 4 million times the mass of the Sun, compressed into a space smaller than the solar system. The conclusion was unavoidable. This was not just evidence of a black hole. It was the most direct proof ever gathered of a supermassive black hole in our cosmic neighborhood. For decades, black holes had lived mostly in theory or at unreachable distances, inferred from powerful X-rays in distant galaxies or explored through equations and simulations. Here, at last, real stars were seen responding to a real gravitational presence, moving in real time around something utterly unseen. As the years passed, the evidence only strengthened. More stars were added to the map. Some traveled farther out. Others skimmed even closer in. All of them told the same story. Their orbits behaved not only as Newtonian gravity predicted, but also showed subtle shifts explained only by Einstein's general theory of relativity. Space and time themselves were bending under the influence of Sagittarius A star. In 2002, Andrea Ghe's team published the first complete orbit of S2. In 2008, Reinhard Genzel's group followed with even more refined measurements. Independent teams, separated by oceans, reached the same conclusion. At the center of the Milky Way sat a massive, invisible object shaping the motion of everything nearby. It could be nothing else. By the 2010s, instruments had grown even more precise, capturing stellar positions down to thousandths of a second of arc, an accuracy comparable to measuring the width of a human hair from several kilometers away. Again and again, the results confirmed what had already become clear. Sagittarius, a star, was real. It warped the space around it. It was a black hole, and still, it remained unseen. Astronomers had traced its influence with exquisite detail. Yet the object itself stayed hidden. Its presence was known through motion, through gravity, through the quiet obedience of stars. Seeing it directly would require an entirely new way of looking. As understanding deepened, scientists also began to place Sagittarius A star into a broader family. Black holes are not all the same. The idea is simple in outline. A region where gravity becomes so strong that nothing escapes. But the ways such regions form and grow vary widely. The smallest are stellar mass black holes, born when massive stars exhaust their fuel and collapse after violent supernova explosions. Though only a few kilometers across, they outweigh the Sun and can shine brightly in X-rays if they pull material from nearby companions. These are scattered throughout galaxies, including our own. Larger still are intermediate mass black holes, hundreds to thousands of times the Sun's mass. Their origins remain uncertain. They may form through repeated mergers inside dense star clusters or through slow growth over long spans of time. They are elusive, rarely observed, and deeply intriguing, perhaps acting as stepping stones toward larger giants. At the top of the scale sit supermassive black holes. weighing millions or even billions of suns. Sagittarius A star belongs here. Though it is modest compared to the largest known examples, such giants could not form in a single collapse. They must have grown gradually, fed by gas, stars, and mergers over cosmic time. Nearly every large galaxy appears to host one at its center, quietly shaping its evolution. There are also types that remain theoretical, primordial black holes, if they exist, would have formed in the earliest moments of the universe, from extreme density fluctuations shortly after the Big Bang. Some might be no larger than an asteroid, others far heavier. Their existence could help explain unexplained cosmic phenomena, but finding them would be extraordinarily difficult. At the extreme end are ultramassive black holes, with masses exceeding 10 billion suns. A few candidates have been identified in enormous galaxies, raising questions about how fast black holes can grow and whether nature imposes an upper limit compared to many of its peers. Sagittarius, a star, is quiet. It feeds only occasionally, producing brief flares in radio, infrared, and X-ray light. This calm makes it harder to spot, yet also makes it an ideal laboratory. Without overwhelming jets or constant eruptions, astronomers can study the black hole itself with fewer distractions. Looking at all these varieties together helps place our galactic center in context. Stellar black holes influence only their immediate surroundings. Intermediate ones may bridge important gaps. Supermassive black holes shape entire galaxies, and primordial ones, if real, could whisper secrets from the universe's first moments. All share one defining trait. Once something crosses their event horizon, it is lost to the observable universe. From our position inside the Milky Way, we cannot see our galaxy from above. We navigate it from within to describe locations. Astronomers use constellations as signposts. Saying something lies in Sagittarius means it appears in that region of the sky, not that it belongs to the constellation itself. When radio astronomers looked toward Sagittarius, they discovered multiple sources clustered near the galactic center. To keep them straight, they named the group Sagittarius A, following the convention of labeling radio sources alphabetically within a constellation. Within that group, Bruce Ballack and Robert Brown identified an especially compact, intense point in the early 1970s. It seemed like a central engine, something deeper and more concentrated than the rest. They gave it a distinctive name, Sagittarius A star, written with an asterisk, borrowed from atomic physics. The symbol suggested an excited or special state. It was not a formal rule, just an intuitive mark. This source felt different, more focused, more mysterious. The name captured that feeling, and it stayed. In the years that followed, as attention slowly gathered around that quiet point at the Milky Way's heart, the name Sagittarius A star settled into common use. It appeared again and again in research papers, telescope logs, and careful notes written late at night in observatories around the world. Even as confidence grew that this object was a black hole weighing millions of times more than the sun, the name remained unchanged. There is a gentle irony in it. The word star, spoken aloud from the small asterisk at the end, belongs to something that is not a star at all. Sagittarius A star does not shine by producing light. It draws light inward. It bends space around itself. Anything that wanders too close is quietly taken in. And yet, the name gives this invisible presence a place on our maps, a way for human language to point towards something otherwise unreachable. Astronomy has always balanced poetry and practicality. Some names, like Betelgeuse or Vega, echo ancient languages and old stories. Others are more utilitarian. Strings of letters and numbers, like Messier 87 or NGC 5128, created by astronomers trying to catalog thousands of faint objects without losing track. When discoveries reach beyond what the eye can see, names often emerge from habit and convenience, with just a hint of imagination. Radio sources, for example, are usually labeled by their position and the order in which they were found. Pulsars, spinning neutron stars that send out rhythmic radio signals, are often identified by coordinates alone. Names that sound more like addresses than characters, yet each name, whether lyrical or plain, helps anchor an idea in the mind. In the case of Sagittarius A star, that simple mark at the end of the name carries unusual weight. It points to something deeper, something shared across the universe. As observations expanded beyond our own galaxy, astronomers began to notice a pattern that was impossible to ignore. Almost every galaxy, regardless of its size or shape, appeared to host a massive black hole at its center. Spiral galaxies, elliptical galaxies, even many irregular ones, all seemed to be built around these hidden anchors. Some central black holes were far larger than Sagittarius A star, others much smaller. But the presence itself was strikingly common. The first strong hints came from galaxies whose cores blazed with extraordinary brightness. These active galactic nuclei emitted more energy than entire collections of stars could reasonably explain. The most convincing answer was that a supermassive black hole was feeding, drawing in gas and dust, and releasing immense energy as that material spiraled inward. The same explanation soon fit quasars, brilliant points of light seen billions of light years away, now understood to be powered by black holes weighing millions or billions of times the mass of the sun. Once astronomers knew what to look for, they began searching for these central giants in quieter, more ordinary galaxies. Again and again, subtle clues appeared, even when a black hole was not actively feeding. Its gravitational pull could still be felt in the motion of nearby stars and clouds of gas. Slowly, it became harder to find galaxies without evidence of such a presence. The question shifted from whether our galaxy had a supermassive black hole to why almost every galaxy seemed to have one. One possibility is that black holes and galaxies formed together, growing side by side from the earliest moments. In the young universe, vast clouds of gas may have collapsed directly into massive black holes, which then continued to grow over billions of years. Another idea suggests that the first generation of stars, far larger and shorter-lived than those we see today, collapsed into heavy seeds that later became supermassive black holes. A crucial clue lies in the surprising relationship between the mass of a galaxy's central black hole and the mass of its bulge, the dense core of stars surrounding it, across galaxies of very different sizes. This relationship holds with remarkable consistency. This suggests a quiet dialogue between galaxies and their black holes. When a black hole feeds aggressively, it can produce winds and jets that push gas outward, slowing the birth of new stars. When a galaxy forms stars rapidly, some of that material may eventually drift inward, nourishing the black hole. The balance is delicate, and the details remain uncertain. What complicates the picture further is timing. Astronomers have observed quasars, powered by black holes containing billions of solar masses, when the universe itself was less than 1 billion years old. To grow so large so quickly challenges existing models and hints that something unusual must have happened early on. In this wider context, Sagittarius A star is relatively modest. The black hole at the center of the galaxy Messier 87, for example, outweighs it by more than 1,000 times. Yet Sagittarius A star fits the same pattern, reminding us that even a galaxy like ours carries this immense presence at its core. There are a few small, faint galaxies where no central black hole has yet been detected. But current limits mean such objects could simply be hiding below our ability to see them. The deeper astronomers look, the more it seems these giants are fundamental to how galaxies live and evolve. They may regulate the flow of gas, influence star formation, and shape the overall structure of their hosts. Sometimes they act like engines, driving dramatic activity. Other times they behave more like silent governors, influencing events without drawing attention to themselves. The fact that their origins remain uncertain keeps the story open. Were black holes born alongside the first galaxies? Or did they emerge later from collapsing stars and mergers? The evidence points in several directions at once. By studying Sagittarius A star in detail, astronomers gain a nearby laboratory for testing ideas about black hole growth and galaxy evolution. Each insight here echoes outward, helping explain distant galaxies whose light has traveled for billions of years to reach us. Even now, the puzzle is far from solved. Knowing the scale of the mystery is itself a step forward. When placed beside the giants of the cosmos, Sagittarius A star reveals its humility. If it somehow replaced the Sun in our solar system, its event horizon would engulf Mercury, Venus, Earth, and Mars without warning, and everything would fade before there was time to react. Yet among the universe's largest black holes, it is not especially dominant. Consider again the black hole in Messier 87, famously imaged in 2019. With a mass of about 6.5 billion suns, it is more than 1,600 times heavier than Sagittarius A star. Its event horizon could contain our entire solar system and far beyond. And even that is not the largest known. At the center of the galaxy, Home 15A, lies a black hole estimated at around 20 billion solar masses. Then, there is TON 618, one of the most massive known objects of its kind. With an estimated mass of roughly 40 billion suns, light would take about a week to cross its event horizon, compared to about 24 seconds for Sagittarius A star. Despite these differences, size alone does not determine danger. A black hole's pull becomes overwhelming only very close to it. Farther away, its gravity behaves like that of any object with the same mass. If the Sun were replaced by a black hole of equal mass, Earth's orbit would remain unchanged. Though the world would grow cold and dark, the same principle holds for galaxies. Larger black holes are not necessarily devouring stars at a greater rate. Activity depends on fuel. Sagittarius A star is quiet because it has little to feed on. Only small amounts of gas and dust drift close enough to matter, producing faint flares in radio, infrared, and X-ray light. In contrast, objects like TON 618 are active quasars, consuming material at a tremendous pace and shining so brightly they outshine entire galaxies. There is evidence that Sagittarius A star may have been more active millions of years ago, possibly producing powerful outbursts that left behind structures such as the vast gamma-ray lobes known as the Fermi bubbles. Today, its subdued nature explains why it remained hidden for so long. Had it been feeding like a quasar, its presence would have been unmistakable, even from 26,000 light-years away. An actively feeding black hole at the center of the Milky Way would have appeared as an overwhelming beacon in the sky. Over time, the calm behavior of Sagittarius A star has become a kind of quiet clue in itself. It suggests that the central region of our galaxy has been living through a relatively peaceful stretch for a very long time, measured not in years, but in the slow breathing of galaxies millions of years at once. Elsewhere in the universe, astronomers see central black holes that behave very differently. Some announce themselves with vast jets, streams of matter and energy reaching outward for thousands of light years. Some inflate enormous bubbles of radio emission that swell into intergalactic space. Some send shock waves through surrounding gas, heating it until it glows. Our own Milky Way offers only softer hints. Like the Fermi bubbles, those faint, towering lobes of gamma-ray emission rising above and below the galactic plane, as if the galaxy once sighed in a brighter voice and then returned to silence. If those bubbles are a lingering footprint of past activity, then Sagittarius A star may simply be between meals, not satisfied forever, not finished, just quiet for now. The region around it is not empty. There are streams of gas, wandering clouds, and stars threading through the crowded heart of the galaxy. Over long enough time, orbital motion makes encounters inevitable. Something will drift a little too close. Something will cross a line it didn't mean to cross. And when that happens, the calm can break. In recent decades, astronomers have caught brief outbursts from Sagittarius A star, sudden spikes of brightness in X-ray and infrared light that last only hours before fading back into the usual dim glow. They look like quick flashes on an otherwise steady horizon, as if the giant stirs in its sleep and then settles again. The simplest explanation is also the most haunting. Small amounts of material fall inward, heat up, and release a momentary flare before disappearing into the dark. It's tempting to think that the great blazing quasars are active only because their black holes are larger. And size does play a role. Many of the most dramatic quasars are powered by black holes billions of times the mass of the Sun, capable of drawing in enormous quantities of matter and radiating far more energy. Sagittarius A star, by comparison, is smaller in the hierarchy of giants, and that may limit how much material it can capture at any given time. Yet size alone does not decide a black hole's temperament. There are black holes with masses similar to Sagittarius A star, some even smaller, that burn far more brightly. The difference, again and again, points back to environment. If the Milky Way's core were richer in gas and dust, the story might feel entirely different. Sagittarius A star could blaze like the heart of an active galaxy, shaping star formation across the Milky Way. altering the chemistry of interstellar clouds and rewriting the look of our night sky. Instead, it lives in a region where fuel is limited and conditions are complicated. That restraint has a strange advantage when astronomers aim their telescopes toward Sagittarius A star. They can study its neighborhood with a clarity that would be impossible if the center were flooded with constant glare. The quiet makes room for precision. It allows the faint motions of nearby stars to be tracked. It lets subtle changes in brightness stand out, not drowned by a permanent storm of light. Even in this subdued state, Sagittarius A star still speaks. It emits radio waves steadily, and it produces occasional flares in X-ray and infrared wavelengths. These flashes are faint compared to the roaring beacons of quasars, but they are precious. For a short time, they offer a closer look at processes near the event horizon, how magnetic fields twist, how turbulence breaks and reforms, how superheated plasma swirls in extreme gravity. There is something quietly unsettling about it, something so massive, so fundamentally intense, and yet so restrained, as if a cosmic predator has chosen not to hunt over the lifespan of a galaxy. This quiet may be only a pause. Feeding habits can shift dramatically across millions of years. Sagittarius A star might remain dim for a very long time, or it might brighten again in some distant era, briefly reshaping the Milky Way's center into something more like the cores we see in active galaxies. This calm may also be one small thread in a larger tapestry of habitability. When a central black hole is highly active, its radiation can influence the galaxy around it. In extreme cases, intense outbursts could strip atmospheres or change the chemistry on planetary surfaces across large distances. Earth sits far from the galactic center, so the direct effects would be softened. But the overall stability of a galaxy may still be shaped by whether its core is quiet or blazing. In that gentle sense, the current calm could be one of many reasons life has had time to grow and endure here. The future of Sagittarius A star depends mostly on whether it finds new food. Our galaxy contains plenty of matter in the broad sense, but close to the black hole, the supply is comparatively sparse. Many stars in the central region travel in stable orbits that keep them safely away. Gas clouds drift through, but not always close enough to be captured over long timescales. Though, galactic dynamics do not stay perfectly neat. A dense cloud passing a little closer than usual, or a star wandering into the wrong place at the wrong time, could provide a sudden meal. Astronomers have watched this possibility approach in real time. A gas cloud known as G2 was tracked as it moved towards Sagittarius A star, and many expected a dramatic brightening when it passed near the center. Instead, the encounter was surprisingly mild. The cloud stretched and distorted, pulled into strange shapes by gravity. But much of it survived. It was a quiet lesson. Not every close approach becomes a feast. Still, the possibility remains. A larger cloud, a denser stream, or a star disrupted by tidal forces could someday deliver far more material than G2 did. If enough matter fell inward, Sagittarius A star could become hundreds or even thousands of times brighter than it is now. The radiation would not arrive at Earth as an immediate threat, but the night sky would change. The galactic center could glow more strongly, perhaps even becoming visible to the naked eye under truly dark conditions. Not as a blazing sun, but as a new prominence in the sky's familiar band. A more dramatic path to activity could come from something the Milky Way has done before and will likely do again, merging far in the future. The Milky Way is expected to collide with the Andromeda Galaxy. The stars themselves will mostly pass by one another without direct impact, separated by the vastness between them, but the gas and dust, less orderly, more easily disturbed, will be stirred, compressed, and funneled toward the center. That kind of inward rush could feed Sagittarius A star heavily enough to push it into a true quasar-like phase. With winds and jets capable of blowing gas outward and slowing star formation nearby, other galaxies show that this sort of transformation is not fantasy. Across the universe, supermassive black holes appear to cycle through active and dormant periods, sometimes roaring, sometimes sleeping, depending on the fuel available around them. The timescales are so large that human history barely registers. Sagittarius A star could remain quiet for 1 million years, or 10 million years, without anyone being surprised on a cosmic calendar. It could also brighten in some future era, perhaps 25 million years from now, during a feeding episode that makes the Milky Way's center look different from anything we have known. There is even the possibility of rarer events, an unusually large infall, the consumption of a dense star cluster, or an encounter with a passing intermediate mass black hole that could release far more energy than the brief flares we see today. Black holes are patient. They do not need to feed constantly. They can wait, and wait, and wait again, until the right conditions arrive. When they do, the shift can happen quickly. That is why astronomers keep watch with many kinds of instruments: space-based X-ray observatories, infrared telescopes, and arrays of radio dishes that listen for changes in the center's quiet voice. Small fluctuations in brightness can hint at material moving inward. Patterns in surrounding gas can preserve the shape of older outflows. The central region can carry a record of past behavior, the way a tree trunk holds rings, subtle, layered, and readable only with care. A new active phase in our own galaxy would be a rare gift to science. Most quasars are so far away that the light we see left them billions of years ago, meaning we are always watching ancient history. Seeing a nearby supermassive black hole brighten dramatically would allow researchers to study black hole feeding and feedback with unmatched detail. As events unfold in a galaxy, we can observe star by star. It would also be a reminder that the Milky Way, for all its familiarity, is still an evolving system, shifting quietly over deep time. One detail has long puzzled astronomers. When people imagine a black hole, they often picture it wrapped in a bright, furious ring of matter, an accretion disk, a swirling structure of gas and dust spiraling inward toward the event horizon. In active galaxies, such disks can glow with astonishing power. Friction and compression heat the infalling material until it radiates intensely, sometimes shining with the brightness of entire galaxies. This is why quasars can be seen from unimaginable distances. So when astronomers look toward Sagittarius A star, they expected to find a clear signature of such a disk. Instead, they found something faint, so faint that for decades it was uncertain how to describe it at all. This absence felt strange, especially because the galactic center is full of stars and threaded with dust lanes and gas structures that seem, from a distance, like plentiful raw material. The answer turned out to be more delicate than a simple "there is no fuel." It lives in the balance of the environment. Radio and X-ray observations suggested that while material does drift toward Sagittarius A star, much of it never completes the final plunge. Instead, the gas heats up, becomes turbulent, and is pushed outward again before crossing the event horizon. This led researchers toward the idea of a radiatively inefficient accretion flow, a situation where matter is too thin, too hot, and too scattered to radiate strongly, and where a large fraction escapes before reaching the deepest region. It is like trying to build a bonfire with wood scattered wide apart. The heat is present, but it cannot concentrate into the bright, steady flame you expected. Around Sagittarius A star, gas can spiral inward loosely, only to be redirected by magnetic fields and turbulent motions, flung back outward in a restless, uneven dance. A bright, flat, neatly defined disk needs a dense and steady supply. In galaxies hosting powerful quasars, that supply often comes from heavy inflows driven by intense activity near the core, sometimes linked to bursts of star formation or the aftermath of galactic collisions. The Milky Way, at least for now, does not provide such a constant river of fuel. Sagittarius A star appears to be living on a trickle. There are hints that this has not always been true. Certain X-ray echoes reflected off nearby gas clouds suggest that a few hundred years ago, the black hole may have been brighter than it is today. If that is correct, then what we see now might be the fading remnant of a more active time, slowly dissipating in the absence of fresh supply. The question grew sharper when the Event Horizon Telescope turned its attention towards Sagittarius A star. This global network of radio telescopes works together like a single Earth-sized observatory, capable of resolving extremely fine structure near a black hole's immediate environment. What emerged was not a clean, bright disk like the one associated with the black hole in Messier 87, but a more irregular, patchy halo evidence of a thin, hot, chaotic flow rather than a dense, shining ring. The faint emissions still mattered. It allowed scientists to estimate temperature, density, and motion in plasma near the event horizon, suggesting conditions that are incredibly hot, tens of millions of degrees, yet too tenuous to blaze like an active quasar. The S-stars, those swift orbiters that pass close to Sagittarius A star, add another quiet complication. Some come near enough that they could shed material into the central region, and yet the accretion flow remains dim. That has led to thoughts about how magnetic fields and turbulence might act like a shifting barrier, deflecting and dispersing much of what tries to fall inward. The disk is not truly missing. It is simply underfed, fragmented, and hard to see unless you know exactly how to look. For now, we live beside a sleeping giant whose hunger is subdued, but not absent. Every so often, the faint glow breaks. A flare appears without warning, as if someone briefly turned up a dim cosmic lantern and then let it fade again. Sometimes the brightness rises many times above its usual level and returns to normal within a couple of hours. There is no fixed schedule, no obvious announcement, because Sagittarius A star is hidden behind thick dust. The suddenness makes these events feel even more mysterious. When they happen, astronomers swing telescopes toward the galactic center, gathering whatever light they can before it slips away. The first time these flares were recognized clearly, scientists were struck by both their intensity and their speed, and the timing suggested that they were coming from very close to the event horizon. The way those flares rise and fall so quickly carries a gentle but powerful hint. If a burst brightens and fades within minutes, the source cannot be sprawling. It has to be compact, no larger than the distance light could travel in just a few minutes. That places the action very close to Sagittarius A star, near the dark boundary where the black hole's influence becomes absolute. No one can point to a single cause with complete certainty, because the region is hidden, chaotic, and always shifting. But there are a few explanations that fit the shape of what we observe. Sometimes, the space around Sagittarius A star is too thin to shine much at all. The gas is there, but scattered, faint, almost reluctant. Then, every so often, a denser clump may drift into the wrong place, perhaps material shed from a nearby star, or a pocket of dust that wandered too close. Gravity catches it, draws it into a tightening spiral, and as it falls, it heats to millions of degrees. For a brief window, it releases energy infrared light, X-rays, radio glow. Then it slips past the point of no return. The flare is what we see of that last bright moment. Another possibility feels almost like weather. But in magnetism, the gas around a black hole is not calm air. It is plasma-charged, restless, threaded with invisible magnetic field lines. Those lines can twist, tangle, and store energy the way a storm cloud stores tension before lightning. If the field lines suddenly reconnect, snapping into a new configuration, they can release that stored energy in a rapid burst. It is similar in spirit to a solar flare on the sun, but happening in a place where gravity and speed are far more extreme. In this view, a flare is not only a sign of matter falling in, but also the sudden uncoiling of pent-up magnetic energy. That helps explain why some flares seem to appear without any obvious warning. There is a third idea, quieter, but always hovering at the edge of possibility. The galactic center is crowded. Stars pass close. Compact objects may drift through. If something ventures too near close enough for tides to pull, hard gravity can tear material loose, shredding it into streams that spiral inward and briefly blaze. These encounters are not expected to happen often, but the center of the Milky Way is a busy place, and often means something different when you're thinking in spans of millions of years, because flares cannot be predicted on a schedule. Observing them becomes a waiting game. Teams watch Sagittarius A star for long stretches, sometimes for weeks, hoping for a single brightening. When it happens, the response has to be quick and coordinated. Telescopes on mountaintops and telescopes in space turn their attention toward the same hidden region, trying to capture the event across as many kinds of light as possible, from radio waves up through infrared and into X-rays, so the flare can be understood as a whole, not just as a single flicker in one band. It's telling that these flares are more often caught in infrared and X-rays than in visible light. That matches what physics expects the hottest, most energetic processes near a black hole naturally radiate more strongly at higher energies. And still, there is no simple pattern. Some flares lean brighter in X-rays, others in infrared. Some vanish in minutes, others linger for hours. The variety suggests that more than one mechanism may be at work. overlapping like different kinds of weather in the same restless sky. One especially memorable brightening occurred in 2019, when Sagittarius A star became brighter than anything recorded from it before, more than twice its previous maximum. For a short moment, it made scientists wonder whether something dramatic had happened, like a star being torn apart. Later evidence pointed instead toward a large clump of gas falling inward, possibly connected to the lingering influence of the object known as G2, which had been moving through the region for years. It was a reminder that even a quiet black hole can still surprise you when conditions briefly align. Those modern flares also invite a deeper question. If this is what Sagittarius A star does while subdued, what might it have looked like when it was truly active? There are hints, soft echoes in X-rays, reflected off nearby clouds, that suggest it may have been far brighter a few hundred years ago, perhaps hundreds of thousands of times more luminous than it is today. If that is true, then today's flares may be small-scale reminders of a more turbulent past, like sparks that linger after an old fire has mostly gone out. For now, the bursts are brief and isolated. But if the environment changes, if a denser cloud arrives, if more gas is funneled inward, Sagittarius A star could feed more vigorously. The occasional flare can feel like a quiet warning, the cosmic equivalent of a stomach growl. Not a feast yet, but a sign that hunger exists. This is why astronomers care so much about the details. Each flare is a natural experiment. By gathering enough of them, by comparing their shapes and colors and timing, scientists hope to narrow down what truly drives them. And the tools watching Sagittarius A star are becoming more capable when observations are combined high-resolution radio arrays, space-based X-ray eyes, sensitive infrared instruments. It becomes possible to follow a flare as it forms, to track how it evolves minute by minute, and to match what is seen to specific physical processes in the plasma just outside the event horizon. Close to that boundary, gravity does not work alone. Magnetic fields matter. They are invisible, but powerful enough to guide and sometimes resist the flow of charged gas. For a long time, magnetism near black holes was treated as background present, but secondary. Now it looks more like a main character. The black hole itself does not generate a magnetic field the way a planet does. The fields come from the plasma around it. As gas moves, it drags magnetic field lines along, stretching and twisting them into complex knots. Near Sagittarius A star, those knots are not neat loops. They are restless and shifting, changing as the surrounding gas collides, heats, and churns. Polarized light has become one of the rare ways to see this hidden architecture. When radio waves are polarized, their orientation carries information about the magnetic fields that shape them. With polarized data, astronomers can infer spiraling patterns in the faint glow around Sagittarius A star, patterns that suggest the fields are strong enough to influence matter, not merely float through it. In a subtle way, gravity and magnetism compete. Gravity pulls inward, patiently and forever. Magnetic pressure can push back, redirect, and sometimes hold material in patterns that delay the final plunge. That competition might help explain why Sagittarius A star is so faint most of the time. If the magnetic fields are arranged in a way that forms a barrier, gas may not fall straight in. It may trickle, swirl, stall, and escape. Yet those same fields can store enormous energy. When they reconnect, when their tangled lines snap and realign, they can accelerate particles and trigger sharp flashes of infrared and X-ray light. Then, the energy dissipates, and the region returns to its dim, steady hush. There is still mystery in how these fields are shaped in 3 dimensions. Some models picture large loops threading far outward through the hot flow of gas. Others imagine a more tangled web where lines constantly break and reform. The hints so far suggest a kind of uneasy balance, some order close to the black hole, more chaos farther out, stable enough to avoid constant eruption, unstable enough to flare now and then. In other black hole systems, strong magnetic structure can help launch jets, narrow beams of plasma flung outward at speeds close to the speed of light. Sagittarius A star does not show an obvious, dramatic jet like the one seen in some active galaxies, but there are hints of smaller outflows, weaker vents that may act like pressure valves. They may carry away energy and gas that would otherwise feed the black hole more directly. In that sense, magnetism could be part of the reason the giant remains so restrained. All of this unfolds near a boundary with a simple name and a profound meaning: the Schwarzschild radius. This is the size of the event horizon, the point where escape becomes impossible. The term comes from the physicist Karl Schwarzschild, who in 1916 found a solution to Einstein's new theory of general relativity that described how space and time behave around a concentrated mass. His work showed that if enough mass is compressed into a small enough region, there is a particular radius where gravity becomes absolute. For a black hole, that radius is, in a practical sense, its size. For Sagittarius, a star, the Schwarzschild radius is roughly 12 million kilometers. In human terms, it is enormous. In cosmic terms, it is surprisingly compact, considering it belongs to an object weighing about 4 million suns. It is only a little more than 17 times the diameter of the Sun, all gathered into an invisible sphere at the heart of the Milky Way. Everything inside that boundary is cut off from the rest of the universe in a very deep way. The event horizon is not a solid surface. It is not a wall you could touch. It is a threshold in the geometry of space and time, where every possible path forward leads inward. From far away, it can be described as a mathematical line. In principle, you could orbit outside it. You could circle it. You could imagine hovering just beyond it with some impossible engine that cancels gravity. But as you draw nearer, the landscape changes. Space itself is falling inward more steeply, and time behaves less like a shared rhythm and more like a private experience. If you were near the horizon, from your own perspective, you might not feel a dramatic moment of crossing, but to an observer far away, you would appear to slow, your light shifting toward red, dimming, fading, as though time itself were stretching like warm taffy. The boundary becomes not only a limit for matter, but a limit for information. Nothing from inside can send a signal outward. In that sense, it is also a boundary for cause and effect. This is why black hole science is so often indirect. We watch the orbits of stars. We measure the motion of hot gas. We study the polarization of light, shaped by magnetic fields. We listen for brief flares that hint at turbulence and reconnection just outside the horizon. Sagittarius, a star, is not unique in having a Schwarzschild radius of this scale. Any black hole with the same mass would share it. What makes Sagittarius A star special is that it is our own galaxy's center. Close enough, in cosmic terms, to be studied in detail compared to most of its distant cousins. Imaging it still demanded extraordinary effort. The Event Horizon Telescope revealed a glowing ring of radio light around a dark center. That darkness is not the black hole itself, but its shadow, a silhouette made slightly larger by the way gravity bends and captures light near the horizon. The true Schwarzschild radius lies just inside that shadow's edge, and because Sagittarius A star is so far away, the whole structure appears in the sky, smaller than a donut on the moon would look from Earth. Capturing it required years of coordination, immense computing power, and timing so precise it had to be anchored to atomic clocks. Beyond the event horizon lies a region we cannot observe directly. General relativity predicts an inevitable inward fall toward what is called a singularity, a place where density becomes extreme and the known laws of physics begin to fail. What truly exists there is unknown. Some ideas suggest quantum effects might soften the collapse, reshaping the center into something different from the classic picture. But as far as observation is concerned, it remains hidden. And yet, just outside that boundary, the universe gives us enough light to study. It gives us faint radio glow from hot plasma. It gives us polarized patterns that trace magnetic fields. It gives us sudden flares that rise and fall like brief thoughts in the dark. It gives us a way to build understanding step by patient step, using instruments that have slowly grown more sensitive and more coordinated across time and distance, from radio dishes to space telescopes. A timeline of discovery. By the middle of the 20th century, the Milky Way's center was still mostly a mystery. It was a direction more than a destination, a bright thickening of the galaxy's pale band, softened by dust and distance. Even after Sagittarius, a star had a name. The true heart of the Milky Way stayed half hidden, like a familiar place seen only through a veil. Through the 1980s, radio astronomy remained the steadiest way to listen. Arrays such as the Very Large Array in New Mexico sharpened the picture and revealed something quietly important. Sagittarius A star was compact, and it was variable. Its radio output rose and fell, not like a steady beacon, but like a low, shifting glow suggesting motion, heat, and change in the plasma around the unseen center. What astronomers wanted most was resolution. To understand something so small and so far away, they needed a way to turn Earth itself into part of the instrument. In the 1990s, very long baseline interferometry began linking radio dishes separated by thousands of kilometers, combining their signals into a single virtual telescope nearly the size of our planet. That immense baseline translated into sharper sight, enough to measure Sagittarius A star's apparent size at the level of tens of micro-arcseconds, an angle so tiny it feels almost like a thought. The meaning was clear, even if the scale was hard to picture. Whatever this source was, it was extremely compact. In that same era, infrared astronomy began to bloom. Better detectors arrived, adaptive optics matured, ground-based telescopes started to pierce the dust with far more clarity, and patient observers traced stars moving in tight, fast orbits around an invisible point. That motion, followed for years, turned into mass, and mass turned into certainty. space-based observatories added their own calm precision. The Chandra X-ray Observatory, launched in 1999, revealed that Sagittarius A star occasionally produces bright flares in X-rays, proof that it was not entirely dormant. The Spitzer Space Telescope mapped the crowded star fields and warm dust near the center with an even steadier hand, freed from atmospheric distortion and the absorption that blurs certain wavelengths on the ground. Each of these instruments, in its own way, cleaned the window. In the 2000s, another band of light became a major tool: sub-millimeter astronomy, a region between infrared and radio that is especially useful for studying cold dust and the faint emission from matter close to a black hole. Arrays in Hawaii, and later, the Atacama Large Millimeter and Sub-Millimeter Array in Chile, provided a sharper look at the galactic center's surroundings. High altitude, dry air, and wide baselines helped researchers tease out fine detail in a glow that would otherwise seem too dim to matter. Still, the most difficult goal remained unchanged: to see the black hole's shadow. The silhouette carved out by gravity near the event horizon, that demanded the most extreme form of very long baseline interferometry. A network spread across the world, synchronized so precisely it could behave like a single instrument. This is where the Event Horizon Telescope emerged. In the 2010s, radio observatories across the globe were linked into one coordinated array, including powerful stations in Chile, a telescope at the South Pole, and others across North America, Europe, and Asia. They observed at a wavelength of 1.3 millimeters, short enough to offer extraordinary resolution, and also able to pass through much of the dust that blocks our view toward the galactic center. In 2017, the network focused fully on Sagittarius A star, but Sagittarius A star does not sit still for a portrait. Matter near the event horizon moves at speeds close to the speed of light, and the brightness pattern can change within minutes. Turning those shifting signals into a single image required careful calibration, complex algorithms, and years of patient computation, blending information across time without erasing the real physics of a restless environment. In 2022, the Event Horizon Telescope team released the first image of Sagittarius A star, a blurry but unmistakable ring of light surrounding a darker center. The shadow, exactly the kind of shape theory predicts for a black hole of this mass. It was not a crisp photograph in the everyday sense, but it was a true image built from real waves of light, gathered across Earth and woven together with disciplined care. The unveiling has never been a single moment. It has been a gradual clearing. New instruments continue to press closer. The James Webb Space Telescope is probing the galactic center in infrared with unmatched sensitivity, while upgrades to the Event Horizon Telescope promise sharper images ahead. With more stations and better coverage, each generation of tools peels away another layer and reveals that the Milky Way's center is not just a static landmark, but a changing part of the galaxy's own story. Alongside engineered tools, nature provides a quieter aid. Light does not always travel through space as straight. In different lines, massive objects curve space-time, and light follows that curvature. This bending, called gravitational lensing, can distort or magnify distant sources, sometimes granting a brief advantage to an observer who happens to be aligned in just the right way near the galactic center. Where stars and dense structures crowd together, lensing can occasionally make faint things more noticeable, or sharpen a measurement at the margins. It is not a guaranteed trick, and it is rarely convenient, because alignment is demanding and often short-lived, but when it happens, it can add a little extra clarity, like a momentary shift in the fog for day-to-day precision from the ground. Though, the most transformative change came from adaptive optics. Starlight passes through Earth's atmosphere before it reaches a telescope, and that atmosphere is always moving. Warm and cool currents bend incoming light in constantly changing ways, making stars shimmer. For casual stargazing, it's beautiful. For tracking tiny motions near Sagittarius A star, it is a serious obstacle. Adaptive optics counters the problem in real time. If the atmosphere bends the light one way, a flexible mirror inside the telescope can bend it the opposite way, canceling much of the distortion. To know how to correct the light, the system needs a reference point. Sometimes that reference is a real bright star. Often it is an artificial one, created by a laser that excites sodium atoms high in the upper atmosphere, producing a glowing point that computers can analyze. The mirror then adjusts hundreds of times each second, shaping itself so the final image steadies. When adaptive optics began to be used routinely on the galactic center, it changed the feeling of the data. Stars that once blurred into one another separated into distinct points. Individual orbits became easier to follow. Subtle shifts in brightness or position became measurable instead of suspected, combined with infrared observations that slipped through dust more easily. Adaptive optics helped turn the center from a shimmering confusion into a place where careful, long-term watching could pay off. Space telescopes still provide unmatched stability, free from atmospheric distortion. But they cannot easily match the mirror size of the largest ground-based observatories. Together, these approaches balance each other: space-based steadiness, Earth-based power, and adaptive optics bridging the atmosphere's restless gap. The result is a view of Sagittarius A star that would have been unthinkable not long ago, and it carried astronomy towards something once considered impossible: the road to the first black hole photo. In 2019, the world finally saw a picture of a black hole's shadow, and it belonged to Messier 87 star. This object is so massive, about 6.5 billion times the mass of the Sun, that its event horizon is enormous compared with Sagittarius A star. That size was one reason it became the first target. A larger black hole casts a larger shadow against the glow around it, and that makes the silhouette easier to capture, even from an almost unimaginable distance. Its great mass also slows the motion of the gas near the edge. The brightness pattern changes over hours or days, not minutes, giving astronomers time to gather data without the scene reshaping too quickly. No single telescope could ever do this. To resolve an event horizon, the instrument would need the sharpness of a telescope as wide as Earth. So scientists did the next best thing. They linked radio observatories across the globe into one synchronized network: the Event Horizon Telescope. Each site watched the same target at the same time, and the combined data behaved like a single planet-sized eye. The precision behind it was almost delicate. The telescopes had to keep time together with atomic clocks so steady they would drift by less than a second over spans of millions of years. Each observatory recorded enormous volumes of information, too much to send over ordinary networks, so the data were stored on specialized drives and physically carried to computing centers for processing. The key observing campaign for Messier 87 star took place in April of 2017. For several nights, every participating telescope aimed at the galaxy, capturing high-frequency radio waves from hot matter swirling near the event horizon. They observed at a wavelength of 1.3 millimeters. And because the network is only as strong as its weakest site, the weather had to cooperate everywhere at once. A storm or heavy clouds at a single location could spoil the run. After the observing nights ended, the real work began. The raw recordings, measured in petabytes, were shipped to powerful computing centers where teams carefully correlated and calibrated the signals. Each telescope had recorded the same sky in its own way, with its own local conditions and tiny timing differences. And those differences had to be matched precisely to reconstruct the interference patterns that carry the image. Even then, the result did not appear like a normal photograph. The Earth-sized virtual telescope still had gaps in its coverage, so algorithms had to infer missing details to keep human expectation from shaping the outcome. Multiple teams worked independently, each building images without seeing the other's results. When the images were finally compared, they aligned closely. On April 10th, 2019, the Event Horizon Telescope revealed the image, a soft ring of light, like a glowing ember, surrounding a darker center. It was the light from superheated matter bent around the event horizon. And the shadow's size and shape matched the predictions of Einstein's general theory of relativity with striking accuracy. That image became iconic because it did two things at once. It confirmed a deep theory in an extreme environment, and it proved a method that many had once doubted. Millimeter wavelength interferometry could, in fact, image black holes. And it opened the door to something that sounds simpler but turned out to be harder: imaging Sagittarius A star. In the sky, our own black hole appears larger than Messier 87 star because it is so much closer. But it is also far more restless. Where Messier 87 star changes slowly, Sagittarius A star changes quickly on the scale of minutes and hours. The gas near its event horizon orbits so fast that the pattern of brightness can shift while the telescopes are still collecting data. Imaging it is less like photographing a still landscape and more like trying to capture a candle flame in an uncertain breeze. Long exposures smear, details blur into motion. There is another complication as well. Messier 87 star lies outside our galaxy, so its radio waves travel mostly through intergalactic space before reaching Earth. Sagittarius A star sits behind the crowded center of the Milky Way. Along the way, its signal passes through turbulent clouds of gas and dust that scatter and soften the radio waves, blurring the view. Scientists can correct for much of this distortion, but not perfectly. Some fine structure is inevitably rubbed smooth because the target shifts so quickly. Timing became even more demanding. All participating telescopes had to capture the same changing scene at nearly the same moments. Even a small mismatch could mean one site was recording a slightly different version of the glow than the others, making the combined image unreliable. Weather became a sharper risk too. The network includes observatories spread from Chile to Hawaii to the South Pole, and Sagittarius A star is visible only during certain shared windows. Clear skies had to align across continents at the same time, over multiple nights, while the target itself kept changing. The imaging approach also had to evolve. The traditional method treated the black hole environment as mostly static during an observing run. That assumption works better for Messier 87 star. For Sagittarius A star, it breaks. Scientists developed new algorithms designed for a morphing target. Instead of producing one single best image from a stable scene, they generated many possible reconstructions and searched for the features that remained consistent across them. Consistency became the proof that something was real and not an artifact of motion. Brightness was another challenge. Sagittarius A star's accretion flow is weak compared to the steady, luminous structure around Messier 87 star. A dimmer source produces a weaker signal, and weak signals are easier to drown in noise. The balance of wavelength was delicate too. At shorter wavelengths, scattering from the galactic plane worsens. At longer wavelengths, scattering eases, but resolution drops. The observing wavelength had to sit at a just right place between clarity and sharpness. On top of that, the line of sight toward the galactic center is busy stars, gas clouds, and other radio sources overlap in the same direction. And separating those signals takes careful filtering and repeated cross-checks. By the time Sagittarius A star's image was ready, the work behind it had become immense petabytes of raw data processed, thousands of simulations run, and countless variations tested. Each step checked and checked again. When the picture was released in 2022, it showed a familiar form, a ring and a shadow, remarkably similar in overall shape to Messier 87 star, yet fuzzier, softer, and more variable, carrying the imprint of a target that never truly sat still. It is easy to imagine Sagittarius A star as the natural next step after Messier 87 star. In reality, it was a leap. The success came from creativity as much as engineering, from coordination as much as machinery, and from a willingness to rethink methods that had worked before but could not work here. And even after that image arrived, the story did not close. For scientists, it was not an ending, but a beginning. The first image confirmed certain expectations, most importantly, that a shadow consistent with a black hole's mass was present. But it also left a long list of unanswered questions. One of the largest is spin. Black holes can rotate at different rates, from nearly none to the fastest allowed by physics. Spin influences how matter orbits, how space is dragged around the black hole, and how jets and outflows might be launched. But a blurry image built from many moments does not easily reveal rotation. For Sagittarius A star, the brightness pattern changes constantly, and the final ring is an average, smoothing away details that might carry the signature of spin. Another uncertainty is orientation. A black hole does not have up and down like a planet, but it does have an axis of rotation. Knowing how that axis is tilted relative to Earth helps scientists understand how matter falls in, how energy might escape, and how the central environment interacts with the galaxy beyond. For Messier 87 star, a visible jet offers a clue. Sagittarius A star has no prominent jet that stands out clearly through the dust and confusion of the galactic center, so its orientation remains harder to pin down. Magnetic fields are another missing piece. Polarized light is one of the best ways to trace magnetic structure. And while follow-up observations focus more strongly on polarization, the first public image did not fully reveal the magnetic architecture surrounding Sagittarius A star. The ring gave a face, but not the full expression. There is also the question of what the black hole looks like in any single instant. If it were possible to take rapid snapshots rather than long averages, we might see hotspots orbiting near the event horizon, shifting patterns in the flow, or flares erupting and fading. But the same high resolution that makes the ring visible also demands long observing runs. And long runs inevitably average the moment-to-moment life away. Even the shadow itself leaves room for wonder. The prediction from general relativity sets a certain shadow size based on mass, and Sagittarius A star's image fits well. But the uncertainty is still wide enough that alternative ideas about gravity are not entirely shut out. Sharper images in the future could tighten those limits, testing whether space-time behaves exactly as Einstein described in this deepest arena. All of this is why the work continues. More observing campaigns are planned with expanded networks and improved sensitivity. There is an ongoing push to capture polarized light more clearly and to extend observing windows so individual features might be tracked rather than blurred into averages. Some researchers are even exploring the idea of adding radio telescopes in space, linking them with ground-based stations to create baselines longer than Earth itself, reaching for an even finer resolution. The first images changed what was possible. The next ones may begin to answer what the first could only hint at. For now, the presence at the center of our galaxy remains partly veiled, not only by the limits of our instruments, but by the nature of the object itself. Even the most remarkable image cannot tell the whole story. A black hole is not something that yields its secrets easily. What lies inside is sealed away, not like an unexplored land waiting for footsteps, but like a box that cannot be opened, no matter how carefully we look at its surface. According to the simplest picture drawn from classical physics, nothing truly orbits once it crosses the event horizon. Space and time bend so completely inward that every possible path leads toward the center. There is no sideways motion in the familiar sense, no circling or lingering. Everything moves forward, and forward only means inward. In that view, the interior is not a place of motion, but of inevitability. Yet modern physics rarely accepts a simple ending. When quantum ideas are brought into the discussion, the singularity itself becomes uncertain. Some theories suggest that the infinite point predicted by general relativity may never actually form. Instead, it could be replaced by something unimaginably small but finite. A dense quantum structure holding mass and energy in a strange, unfamiliar state. If so, the interior might not be a single destination, but a layered region where geometry behaves in unexpected ways. In some speculative models, passing the event horizon leads not directly to a final collapse, but to another boundary, an inner horizon where space-time changes character again. Within such regions, mathematics allows for paths that loop or oscillate, though they would bear no resemblance to planetary orbits. These are not journeys through space as we know it, but movements through warped geometry, hidden forever from the outside. Other ideas imagine interiors shaped by exotic forms of matter. In certain versions of string theory, the inside of a black hole might be filled with tangled networks of vibrating strings or membranes. Motion there would not follow smooth curves at all, but repeating patterns defined by the structure of space-time itself. Quantum mechanics adds another layer, with virtual particles briefly flickering into and out of existence near the horizon. These effects are tied to Hawking radiation, the slow leakage of energy that could, over unimaginable spans of time, cause a black hole to fade inside. Such fluctuations might create a restless, invisible sea of momentary structures, appearing and vanishing before anything like a stable orbit could form. There are even ideas that step further outward in imagination. Some propose that the interior of a black hole might not belong to our universe at all. Matter falling in could be funneled into a new region of space-time, perhaps even the seed of another universe. In these models, paths inside might curve not around a center, but through tunnels of geometry that connect distant realms. Whether such structures could exist stably is deeply uncertain, but the mathematics does not forbid them outright. Another line of thought focuses not on matter, but on information. The question of whether information is destroyed inside a black hole remains unresolved. Some theories suggest that information could be preserved in subtle patterns within the interior. If so, those patterns might evolve, interact, and repeat, forming cycles that resemble motion, even though no signal from them could ever escape. In loop quantum gravity, space-time itself is made of tiny, discrete units inside a black hole. These units might rearrange in a way that prevents total collapse. Instead of falling endlessly inward, matter could rebound, creating oscillations deep within. In such a picture, motion comes not from gravity pulling objects around, but from the geometry of space itself, shifting and repeating. All of these ideas face the same unbreakable boundary. The event horizon blocks direct observation. No future telescope, no matter how powerful, can look past it. The only way forward is indirect, through mathematics, simulations, and careful study of how the black hole influences its surroundings. Still, asking what might be inside matters. It forces physics to test itself at the edge of what it claims to understand, and to question whether space and time are truly what they appear to be. That same spirit of questioning applies to what Sagittarius A star actually is. The evidence that it is a supermassive black hole is overwhelming. Stars race around an invisible point at extreme speeds. Gas and dust heat and glow exactly as expected when falling toward an event horizon. Yet science advances by challenging even its strongest conclusions. So alternatives have been explored. One suggestion is that the central object could be a dense concentration of dark matter. Dark matter reveals itself only through gravity, and it dominates the mass of the universe. In principle, a massive dark core could pull on stars in the same way, but dark matter does not easily shed energy. Without a way to cool and collapse, it would remain spread out. Observations show that the central mass of the Milky Way is extraordinarily compact, far denser than any known form of dark matter could achieve. More exotic possibilities exist. Some theories propose new kinds of dark matter that interact more strongly with themselves, allowing them to clump tightly. Such objects might mimic a black hole's gravity without forming an event horizon. But if a surface existed, infalling matter would crash into it and release energy. No such signal has been seen. Another proposal is the boson star, an object made of particles that follow different rules than ordinary matter. Under certain conditions, these particles could form a dense, star-like structure without an event horizon. From far away, it might bend light in a way that looks almost identical to a black hole. Subtle differences could exist in how matter behaves near it, but detecting those differences would require sharper images and finer timing than we currently possess. There is also the gravistar idea, where collapse halts just short of forming a black hole, creating a shell of exotic matter surrounding a strange interior. From the outside, it would appear nearly indistinguishable from a black hole, but without a true horizon. Again, no clear evidence has been found to support this. More speculative ideas still exist, from fuzzball models to wormhole entrances, but all share the same problem. Sagittarius A star behaves exactly as a black hole should. Every observation so far fits that description, until a clear contradiction appears. The simplest explanation remains the strongest. Beyond its identity, there is the question of influence. The Milky Way's inner regions are nothing like the calm neighborhood where our sun resides. Near the center, stars move fast, sometimes completing an orbit in just a few years. In the early universe, the Milky Way was chaotic, filled with merging clouds and fragments. Sagittarius, a star, likely began as a smaller object. Growing as matter fell inward, its gravity deepened the central potential, helping shape the dense bulge of stars. At times, that growth may have fed back into the galaxy itself. When active, the black hole could have heated or expelled gas, slowing star formation in some regions, while allowing structure to emerge over longer timescales. The relationship between black hole mass and galactic bulge mass suggests a shared history, a quiet partnership across billions of years. Signs like the Fermi bubbles hint that Sagittarius A star's reach extended far beyond the immediate center. Its gravity fades with distance, but its influence may have shaped how matter settled, how stars formed, and how the Milky Way became the galaxy we inhabit today. Even now, long after its most active periods, that hidden presence continues to define the shape of our home, quietly holding the center while the spiral arms turn around it. The pull of Sagittarius A star is strongest close to the center. Then it thins with distance, fading into the wider gravity of the Milky Way itself. And yet, the heart of a galaxy is more than a point mass. Around Sagittarius A star, there is a dense cluster of stars, gas, and compact remnants, an entire crowded core whose combined weight shapes the inner Milky Way like a heavy knot in a long fabric. Some researchers think that this central concentration, the black hole plus its surrounding star cluster, has helped the Milky Way maintain one of its most striking features: the galactic bar. The bar is a long, bright band of stars cutting across the center, a structure that acts like a slow conveyor belt. Over time, it can funnel gas inward, feeding the inner regions where new stars are born, and occasionally delivering fresh material toward the black hole as well. It is not a fast, dramatic process. It is steady, patient, and it can quietly reshape where the galaxy keeps its fuel. If the bar helps guide gas inward, then Sagittarius A star and its neighborhood may be part of a larger cycle: gravity organizing motion, motion guiding gas, gas turning into stars, and stars returning material back into the interstellar medium. In that sense, the black hole's influence does not have to reach the outer disk directly to matter. It may act through structure, through the way the galaxy's inner regions keep themselves arranged. There is also a softer influence that can build over time: chemistry. The Milky Way did not begin with the rich palette of elements we see today. Carbon, oxygen, iron, and many other heavy elements are made in stars and spread by stellar winds and supernovae, then recycled into new generations of stars and planets. If Sagittarius A star's activity affected where and when stars formed near the center by heating gas, clearing it out, or disturbing it, then it could have indirectly shaped how those elements were mixed and redistributed in regions where energetic outbursts pushed gas away. Star formation might have paused, delaying the local recycling of heavy elements over billions of years. Those delays and bursts could contribute to the chemical variety astronomers measure across the galaxy today. The quiet differences that tell us where matter has been and what it has endured. Still, there are clear limits. The Milky Way is vast. The outer disk lies so far from Sagittarius A star that the black hole's gravity is barely distinguishable from the general mass of the galaxy. The spiral arms where our sun lives are shaped more by density waves and the overall rotation of the disk than by anything happening at the core. The center may sculpt the bulge and inner structure, but the broad, sweeping arms likely grew from other processes, gravity spread across billions of stars. The slow settling of matter, and the long, rippling patterns that move through a rotating disk like a persistent tide. The early Milky Way has changed beyond recognition. Much of the direct evidence is gone, buried in the motions and chemical fingerprints of stars we see now. That is why astronomers study other galaxies at different stages of growth, looking for living snapshots of what our own might have looked like billions of years ago, and for the subtle signatures of central black holes shaping their hosts. Some models suggest that without a central black hole, a galaxy like the Milky Way might have formed with a smaller bulge or a less organized inner region. Others argue that black holes and galaxies grow together through feedback rather than design a conversation, not a blueprint. In that view, Sagittarius A star shaped the Milky Way's heart, but the galaxy's overall form came from a blend of rotation, gravity, mergers, and time. The truth may rest in the middle. Sagittarius A star was likely both passenger and driver, sometimes quiet, sometimes influential, leaving marks we can still try to trace in the galaxy's inner architecture. And while our understanding deepens, the instruments watching this region are also changing. The image we have now, astonishing as it is, was built with technology that has already begun to evolve. Astronomy moves with an unusual rhythm. The moment of observation and the moment of publication are often separated by years. By the time the first image of Sagittarius A star reached the public, the tools that made it were already being upgraded. The next major step forward for the Event Horizon Telescope will come from adding more stations. Each telescope in the network is like another point on a vast, invisible mirror. The more points you have, the more complete the picture becomes. Right now, there are gaps, because telescopes can only be placed where geography, funding, and agreements allow. New sites in regions not currently covered would fill in missing parts of the pattern, sharpening the reconstructed image. Proposals include additional stations in Africa to strengthen coverage of the southern sky, and ideas for new sites on Pacific islands or even platforms at sea, placed where they can catch pieces of the signal current stations miss. There is also a more daring possibility: taking part of the network off the planet entirely. Space-based radio telescopes could work with ground stations to create baselines larger than Earth. Space Very Long Baseline Interferometry has been tested before. But black hole imaging would push it far harder. If it becomes practical, the gain in resolution could be dramatic enough, perhaps, to see changes in Sagittarius A star's surrounding glow over shorter timescales, turning the first still frame into something closer to motion. Data handling will change as well. Today, the Event Horizon Telescope generates immense volumes of recording, and moving that data is a project of its own. Future systems will use faster, higher capacity recording, and may allow more direct transfer between sites using ultra-high-speed links, reducing the long delays between observation and processing. Computing will advance too. The next generation of imaging will rely on improved algorithms, and some of them may be guided by machine learning tools that can recognize patterns in interference data quickly and help identify which features remain stable across many reconstructions. This does not replace careful physics. It simply adds another layer of precision and speed to the process, allowing scientists to test more possibilities and catch subtle changes sooner. Even the way the network observes will broaden. The Event Horizon Telescope first worked mainly at a wavelength of 1.3 millimeters, a sweet spot that balances resolution with atmospheric transparency. But that is only one slice of the spectrum. Observing at multiple wavelengths can reveal different layers of the environment: hotter plasma closer in, cooler material farther out. Shorter wavelengths, such as 0.87 millimeters, could sharpen images further. Though they require extremely stable equipment and excellent conditions, longer wavelengths can reduce certain scattering effects, but also reduce resolution. Using several bands together begins to create something like color information for black holes. Not invisible hues, but in physical layers, temperature, density, and motion teased apart. Longer observing campaigns will matter too. The first image of Sagittarius A star relied on only a few nights, because all sites needed clear skies at the same time. Better scheduling and improved forecasting may help gather more consistent data across more nights. More data means not only sharper images, but the possibility of tracking change, watching bright regions move, fade, and reform. The long-term dream is a movie plasma swirling around the event horizon, not as a simulation, but as an observed dance. Other instruments may join the effort in different ways. The Square Kilometre Array, planned across Australia and South Africa, is designed for immense sensitivity rather than event horizon resolution. But linking its power into global networks could help detect fainter features, smaller flares, thinner streams of plasma, subtler variations in brightness, and farther out on the horizon of imagination. Some talk about radio telescopes on the moon, where the lack of atmosphere would remove a major source of distortion and allow steadier observing. A lunar station paired with Earth-based sites would create an even larger virtual dish, sharpening the view again. As images improve, polarization will become increasingly important. The first image of Messier 87 star included a polarization map that traced magnetic field structure, and similar work is being pursued for Sagittarius A star. Better polarization data could reveal how magnetic fields twist, break, and reconnect processes that may explain why Sagittarius A star is usually quiet, and why it sometimes flares. Among the most delicate properties scientists want to uncover is spin. How fast Sagittarius A star rotates could tell us something about its history, whether it grew slowly over billions of years by swallowing small amounts of matter, or whether it gained mass in more chaotic events, perhaps including mergers with other black holes. Spin cannot be seen directly. It must be inferred from how light and matter behave in the warped space near the event horizon. One of the most promising ways to do this is X-ray polarimetry. Polarimetry measures the orientation of light waves, certain processes scattering, magnetic fields. Strong gravity can align that orientation in characteristic ways. X-rays emitted near a black hole can carry these fingerprints. If Sagittarius A star is spinning, it drags space-time around with it, an effect called frame dragging. That twisting changes how X-rays move, scatter, and escape, and it can imprint patterns in polarization that careful instruments might read. For a long time, X-ray polarimetry was more hope than tool. Measuring X-ray polarization requires detectors that can record not only a photon's energy and arrival direction, but also the orientation of its electric field, an extraordinarily demanding measurement. Because Earth's atmosphere blocks X-rays, this work must be done above the air, using satellites or high-altitude platforms. NASA's Imaging X-ray Polarimetry Explorer, launched in December of 2021, is one of the first missions built specifically for this purpose. It has already measured polarization from several energetic objects. Sagittarius A star is a challenging target because it is faint in X-rays most of the time. But during flares, its signal may become strong enough to attempt meaningful polarimetric readings. Future concepts involve larger collecting areas to gather more photons, sharper imaging to separate the black hole's emission from the crowded galactic center, and faster timing to track how polarization changes during a flare. If scientists can watch the polarization angle swing as matter orbits close to the event horizon, they may be able to estimate not only spin, but also the tilt of the rotation axis relative to the galaxy. Spin could also be a fossil record. If it is high and aligned with the Milky Way's disk, it may suggest long-term feeding from the galaxy's own material. If it is low or tilted oddly, it could hint at a history of chaotic mergers and misaligned infall. Polarimetry also offers a way to test general relativity in the strong gravity regime. Einstein's equations predict specific relationships between spin, warped spacetime, and the polarization of escaping light. If measurements disagree, it could point toward new physics, or toward effects we have not yet accounted for. Polarization can even help separate the influence of gravity from the influence of magnetic fields, because both can polarize light, but in different ways. By comparing polarization across different X-ray energies, researchers may begin to disentangle the two, revealing a clearer map of the environment. And beyond light, there is another messenger many hope to hear one day: gravitational waves. A stable black hole like Sagittarius A star does not produce strong, detectable gravitational waves by itself to make space-time ring loudly enough for us to listen. Something dramatic must happen, and in spiral. A merger, a compact object falling inward. One of the most promising scenarios is an extreme mass ratio in spiral, often shortened to EMRI. This is when a much smaller object, a star, or a smaller black hole with a mass of a few tens of suns, gets trapped and slowly spirals inward towards Sagittarius A star over very long periods. As it draws closer, its orbit tightens and speeds up, and the ripples it makes in space-time become stronger and more complex. Near the final stage, before it crosses the event horizon, the gravitational wave signal would carry a uniquely detailed fingerprint of the space-time around Sagittarius A star. These signals would be too low in frequency for current ground-based detectors such as LIGO and Virgo, which are tuned for higher frequency events like collisions between stellar mass black holes. But a future space-based observatory, such as the European Space Agency's planned Laser Interferometer Space Antenna, often called LISA, is designed to listen in that lower frequency range, where the slow, deep murmurs of massive systems can be heard. LISA, short for Laser Interferometer Space Antenna, is being designed to listen for gravitational waves in the millihertz range. These are the slow, deep murmurs that an extreme mass ratio and spiral would produce a small object, like a stellar mass black hole or a neutron star, slowly spiraling toward a supermassive black hole. Instead of mirrors on Earth, LISA will use 3 spacecraft flying in formation, separated by millions of kilometers, linked by laser beams. With that immense spacing, the mission can sense long, drawn-out stretches of space-time being gently compressed and stretched as massive bodies orbit. If, one day, a compact object becomes trapped in a long death spiral towards Sagittarius A star, LISA could, in principle, detect the signal years before the final plunge. That early warning would be precious. It would give astronomers time to coordinate observations across the spectrum, from radio to infrared to X-rays, watching the galactic center with a kind of quiet readiness, waiting for the moment when gravity's song grows louder. There are other possibilities. 2. A sudden collapse of a massive star near the galactic center, or a neutron star being torn apart by tidal forces, could generate short, violent bursts. Those would sit in higher frequency ranges, better suited to ground-based detectors. But such events are rare, unpredictable, and would require extraordinary luck to happen close enough, at the right time, while instruments are watching. If we ever do catch gravitational waves tied to Sagittarius A star, the payoff would be enormous. Light is beautiful, but it can be scattered, absorbed, and distorted by dust, gas, and magnetic storms. Gravitational waves pass through matter almost untouched. They could give a cleaner view of the space-time just outside the event horizon, and they could measure mass and spin with a precision far beyond what we can infer from images alone. They could also test general relativity in the strongest gravitational field we are likely to probe. If the signal deviated from predictions, it could point to new physics, something subtle and unexpected in the geometry of space-time. This kind of listening is not easy. The signals can last months or years, buried in noise, requiring long observation and extremely careful analysis. Timing matters, especially if we want to match a gravitational wave detection to what telescopes see at the same time. That is why missions like LISA are being planned for the 1930s decade or later. There is a great deal of engineering between an elegant concept and a delicate instrument operating in deep space. Ground-based observatories are also being upgraded. Next-generation projects aim to push sensitivity far beyond what we have now. They will not be tuned to the slow spirals into Sagittarius A star, but they could catch shorter bursts from sudden disruptions near the galactic center. Taken together, space-based listeners for low frequencies, ground-based listeners for higher ones, This future network could cover a wider range of cosmic events, filling out the gravitational wave spectrum the way radio arrays fill out a sky map, looking even farther ahead. Some imagine multiple space-based observatories spread through the solar system, working together the way very long, baseline interferometry links telescopes across Earth. With several detectors, we could triangulate sources with much greater precision, pointing our telescopes quickly and confidently whenever something stirs near the galaxy's core. The idea of hearing Sagittarius A star is still in the future, but it no longer feels like pure science fiction. The first steps are already being laid, and then there is a more distant chapter in the Milky Way's life, one written not in years, but in billions of years. A collision waits on the horizon of time, the Milky Way and the Andromeda galaxy drifting toward each other. Drawn together by gravity, the approach is slow by everyday standards, yet inexorable on cosmic ones. In roughly 4 billion years, the two galaxies are expected to begin their long interaction, less a crash, more a gradual blending, a repeated weaving together of stars, gas, and dark matter. When people imagine galaxies colliding, they often picture stars smashing like billiard balls. But stars are separated by such enormous distances that direct collisions are unlikely. The real drama is in gravity's rearrangement spiral arms stretched and twisted, gas clouds compressed and stirred, orbits reshaped, star formation ignited in new places. Over time, the neat disk structure of the Milky Way will not survive unchanged. Simulations suggest the merged system may settle into something more like an elliptical galaxy rounder, with less distinct spiral arms, its stars moving in more varied, less orderly paths. At the heart of that future encounter will be two supermassive black holes, Sagittarius A star and the black hole in Andromeda's center. As the galaxies merge, those central giants will slowly migrate toward each other through dynamical friction, a kind of gravitational drag caused by the surrounding sea of stars and dark matter. Their approach would likely be accompanied by a flood of disrupted gas and dust funneling inward, potentially feeding both black holes and lighting them up as active galactic nuclei. If that happens, the core of the merged galaxy could blaze, not because the black holes themselves shine, but because matter around them heats, glows, and radiates as it spirals toward the edge of no return. For tens of millions of years, the two black holes could orbit each other, gradually losing energy through gravitational waves, tightening their spiral until the final merger. That last moment would release an immense burst of gravitational energy and leave behind a single, larger black hole, its final mass and spin shaped by the long history of both galaxies. In a sense, the rotation of the new central object would carry a record of the entire cosmic dance that created it. Whether any life would witness this is another question entirely. 4 billion years is nearly the span of time since life first appeared on Earth. Over that kind of timescale, the sun itself will not remain as it is. Long before the galaxies fully merge, our star's slow brightening is expected to make Earth's surface increasingly hostile. Oceans could evaporate. Water could be lost to space. The planet may cease to be habitable well before the Milky Way and Andromeda truly entwine. Even if the sun's changes were somehow avoided, the merger would scatter stars into new orbits. Our solar system could be nudged outward, or inward, or left mostly alone, depending on an intricate chain of gravitational encounters. The most likely outcome is not catastrophe by collision, but relocation, our sky rewritten, our neighborhood changed, our familiar constellations dissolved into something new. Later still, around 5 billion years from now, the sun is expected to swell into a red giant. Its outer layers may engulf the inner planets, and Earth could be consumed or scorched beyond recognition. By the time the central black holes finally merge, the sun may already have become a white dwarf, leaving Earth, if it remains at all, a silent relic. So the honest answer is that Earth is unlikely to be here in a living, watching sense. Yet the universe does not require witnesses. The galaxies will meet. Their stars will weave through one another. Their cores will slowly fall together, and the Milky Way, as we know it, will be transformed into something new, whether anyone is standing under a sky to notice, or whether the story continues only as a quiet fact of physics.